All right, so I want to take a few moments to talk about the setup for a logistic regression and why we have it set up that way. All right, so you may have seen this relationship here, and this is what I'm going to discuss. Why is it that we set up our logistic regression like this? So we have yi. These are our outcome variables, right? And they take values 0 or 1. So they're binary, okay? So yi is binary. That's an important first step for using logistic regression, okay? Then the probability that yi equals 1, we are using this notation that it is pi of xi. So xi are our independent variables that we are using to try to predict the probability that y equals 1. Ultimately, that's what we want to know. We want to know how to predict the probability that someone has a disease, for example, versus does not have a disease. Okay? And so we have these independent variables that are going to help us out to do that. All right? Now, yi is following a Bernoulli distribution because Bernoulli is a distribution that has binary outcomes. Okay, so we didn't have to use Bernoulli, but we're using it because it has binary outcomes. All right, so then we say, all right, well, pi or pi of xi is equal to all this jazz over here. Okay, 1 over 1 plus e to the power of negative xi transpose times beta. Okay, so where did this come from? All right, so why is it that we are setting it up like this? Well, ultimately what we want to do is we want to be able to predict the probability that yi equals 1. This is what we want. We want to be able to predict this, right? And this is it is restricted. It must be between 0 and 1 because probability must be between 0 and 1. Okay, so when we're modeling this, if we were to use like a linear model where we just have xi transpose times beta, right? By the way, I'm using vector notation. Don't let that throw you. This is basically the same thing as beta naught plus beta 1 times x1i plus beta 2 times x2i plus ... beta p x pi, right? So I'm using vector notation where this little sideways arrow thing means that I'm using a vector, and it is 1, x1i, x2i, xpi, okay? And beta is beta naught, beta 1, beta 2, beta p, okay? Okay, so why not just have this, the probability that y equals 1 just equal this? Well, this guy is not restricted to be in between 0 and 1, right? So like if I were to try to run just like this is basically like, looks like a linear regression, you can. That's kind of what discriminant analysis is. So in that case, you would have on the y-axis, you would have the probability that y equals 1, and say on the x-axis you had one of the x values. So you could plot the probability that y equals 1. It would range from, your data would range from 0 to 1, okay? And say, it was something like this. Then when you go and you find your model then would maybe look like this, right? And so this would potentially work as long as x is, in an area where it makes sense, where the model makes sense. But what if now x is some value over here, and your model now is saying that the probability that y equals 1 is beyond 1, right? And so that's not possible, All right. So what we want to do is we want to be able to construct a way to model this where I'm still within 0 and 1. Okay. And that's where the logic function comes in. So then this is where the logic function comes in to help us. All right, and what is the logic function? It says that the, so it's logit, okay, of the probability that y equals 1, yi equals 1, equals the log that the probability that yi equals 1 divided by the probability that yi equals 0. Okay, so this is the logit function. And the reason why we use this is because now this guy, you can show that it will range from, it can possibly range from negative infinity to infinity, right? So now when I model that this equals xi transpose times beta, I'm not going to have this problem of being outside the range of possibilities. Okay, so that kind of solved that problem. That's why we use this function. This is kind of a smart way to kind of get around this issue that the probability of y equals 1 has to be some number between 0 and 1. All right, so that doesn't explain how I got here. How do I get here? How do I get here? Where'd this come from? All right, so it does follow from this. All right, so now it's just a bunch of math to kind of show that. So let's start with the log. Now the probability of y equals 1, this is pi of xi. Okay, and the probability that y equals 0 would just be 1 minus pi of xi. Okay, so this is the way I've defined pi of xi. It's equal to the probability that y equals 1. All right. So now we can show that pi of xi is this relationship right here. I just kind of have to do some math. So first, let me go ahead and take e for both sides. Okay. So the e and the log cancel. Okay, and I end up with pi of xi 1 minus pi of xi equals e to the power of xi transpose times beta. Okay, so now I just need to do some math to solve for pi of xi. All right, so let's go ahead and multiply both sides by the denominator. So I have pi of xi equals 1 minus pi of xi times e to the power of xi transpose times beta. Okay, so I have parentheses here for that guy. Then go ahead and distribute. All right, so this equals e to the power of xi transpose times beta minus pi of xi times e to the power of xi transpose times beta. All right, so all I've done is distribute. All right, so now, so remember my goal is to get pi of xi by itself. So let's go ahead and bring this over to this side of the equation. So I have pi of xi plus pi of xi transpose, or sorry, pi of xi times e to the power of xi transpose times beta. Okay, so I'm basically adding this term to both sides of the equation. Xi times beta. Okay, so now let's take this guy and pull him out. So I end up with 1 plus, right? So I'm pulling him out. 1 plus e to the power of xi transpose times beta. Okay. Okay, we're almost there. So now to solve for pi of xi. I just need to divide both sides by this piece here. So I have pi of xi equals, I have this in the numerator, divided by 1 plus e xi transpose times beta. Okay, so I've solved for pi of xi, but if you go up to the top, that's still not what I have up here. Right? A lot of times it's better to write this like what I have here when I'm finding my likelihood function. So how do I show that those two things are the same? Well, if I were to divide both the numerator by e to the power of xi transpose times beta. So if I divide that by the numerator, I also divide that in the denominator. All right, so I haven't done anything. Basically, I am dividing both the numerator and denominator by the same thing. So that's basically dividing, multiplying it by 1. So I'm not actually doing anything, right? But what I am doing is going to simplify some stuff. So this then cancels with this, okay? And what do I have? So in the numerator, I'll have 1, okay? In the denominator, I have something like a compound denominator, because I have this guy being divided by this guy. All right. So I'm going to divide both the 1 and this guy. All right. So I end up with 1 over 1 xi transpose times beta. So, okay, plus e to the power of xi transpose times beta divided by e to the power of xi transpose times beta. Okay, so I'm just using my properties of how to do when I have an addition sign up on the numerator and then this on the denominator, how to break that up. Okay, so then these guys cancel each other, and this is equal to 1, right? And then this is the negative power, because this is e, so it's 1 over e to the power of this guy, which is the same thing as having a negative exponent. So this is e to the power of negative xi transpose times beta, okay, plus 1. Right, which I think in the beginning of this video I had it the other way around, which is exactly the same. Okay, so it's just some math that you have to do to kind of get from the logit function to this equation here. All right, so hopefully that makes sense, and thanks for watching.